Okay, so today we start our next topic, and today we will be discussing support vector machines. Maybe you have heard something about support vector machines, maybe not, but I'll try to explain them to you and give you some sort of mathematical background and what is behind the stages of the support vector machines. First of all, what is a support vector machine in terms of machine learning? So we all remember that we have some sort of classification of problems of machine learning, and we remember that our first, let's say, point of branching is the point where we say is our problem supervised learning, unsupervised learning, so on and so forth. So support vector machines, it's a supervised learning, and moreover our supervised learning is then has two sub-branches, and you probably remember that one of the sub-branches is classification and the other one is regression. So today we have a classification problem. So supervised learning, classification. A support vector machine is in some sense very powerful and versatile model. So it is capable of performing not only classification, despite the fact that I will be mostly focusing on the problem of classification, but it is capable of performing even regression, some sort of outlier detection, and some different things. So I guess we will get to that. But in the beginning, I wanted to know that this model is quite powerful. It has some sort of interesting story behind it, because in before 1980s, almost all learning methods they some sort of learned so-called linear decision surfaces. And these linear methods, they have nice theoretical properties, but in fact there are some sort of problems with that, because not so many data sets are suitable for this sort of linear separation. In 1980s, decision trees emerge, and we see some sort of neural networks, and everything is starting developing. And interesting that in 1990s, even later than neural networks, efficient learning algorithms for some sort of nonlinear functions are emerging, and support vector machine is one of such, let's say, idea and one of such methods. So what I will show you today, of course, is the fact that support vector machine is not only capable of solving the problem of separation of linearly separable data set, but besides that, you can separate even features, even data points that are not linearly separable. And that's why this is a very powerful method, because if we were able to work only with linearly separable data sets, I don't think anyone would use this method. It's really hard to find such sort of data set, and it's not very common in practice. But this thing is capable of performing classification even with highly nonlinear data sets, and we will make some use of that. Okay, now let's get to the problem itself. So first of all, I want to draw you a little picture, and I'll try to state this problem in some sort of way, let's say, with a picture. So suppose I have data points that live in two-dimensional space. The axes in this space, they designate some sort of features. So this is my feature 1, and this is my feature 2. And suppose I have a data set that looks something like this. So some points here and some points here. Now, what I want my method to do, I want to separate these points. This is a very nice case. This is a very nice case in a sense that this data set is linearly separable. So you can separate these points with just drawing some straight line that passes somewhere, I don't know, maybe somewhere here. Now an interesting, let's say an interesting question for you. How do you think if I'm drawing this sort of line? So I'm separating these points, but I can draw a line in a very different fashion. So for example, I can draw it like this, or I can draw it like this. I often ask someone to think which of these lines will we consider the most natural way to divide the plane into parts and separate these points. So let me enumerate them. Which one looks for you the most like natural way?
Line number 2.
Line number 2, yes. So we all think that line number 2 is, in some sense, the most natural way to separate this data set into two parts. Why do we think so?
Because it divides the space of halves, most looking like halves of parts.
Well, each of these lines is dividing our space into two parts. Moreover, they are all very nice in a sense that they split our data set into two parts, from which one contains only one class black and the other one contains class blue. But we all intuitively, for some reason, we want to choose line number 2. Well, maybe the most I say natural way to express that is the fact that this line number 2 is in some sense the farthest line from our points from our data set, and still separating this data set into two parts. So if I'm trying to get to points from the data set from the line number 2, you see that these points and these points are quite far from the line number 2. So what we want to draw a line that is not only separating our points, but it lies from these points quite far away. Okay, let's try to think about this problem. So let me remove all the redundant lines. Okay, so let's reiterate. So what I'm trying to teach you with this example. So with this example, I'm trying to introduce to you support vector machines, but in some sort of intuitive way. So I'll be trying to get together to one point our intuitive ideas about separating some sort of points on a plane in a very simplified case. I will show you much more complicated cases later, but we should always start with some sort of simple case. The simplest thing we start from, the easiest is to solve this problem. Of course, then we will need somehow to make it more general. So we will need to generalize our solution to get somewhere to more complicated data sets. But let's start with this simple one. And I'm trying to get to one point our intuitive ideas and some sort of mathematical analytics. So that's the way we want to go. And the first thing, I need some, so I have this sort of data set, and I have some intuitive idea that I want to draw a line that is separating these points. So on the one side of this line, one class lies, on the other side will lie the other class. And I want this line to be as far from these points as possible. Let's try to express that in some formula. First of all, I will draw a line, so I need some analytical expression for the line. Which analytical expressions for the line do you know? So how can I express a line in some sort of mathematical fashion? Yes, so that's one possible way. So I can express that as y equals kx plus b. One of the methods I don't like the most, probably. Maybe I will show you sometimes why. It's
with a parameter?
Yes, so we can express that in some sort of more vector way with a parameter. So I can say that, I don't know, some vector L, let's say it's some parameter t times vector v plus, I don't know, some v0. So that's okay. So we have these sort of expressions. For this problem, we will find quite convenient one more method of expressing the idea that points are lying on the line. So here it is. If I have some line, so here's my line. Let me take some normal vector to this line and call it a w. I will suppose that my w is unitary, so that's for convenience. Now, what can we tell about the points on this line? Let me draw this thing right here. It's one more perpendicular, and I suppose its length is equal, for example, to b. Now, what can I tell about any point that lies on this line? What's so special about these points? So we have a vector w.
From the point where our normal vector started, like we draw a vector from this point where the normal is to that point x, and such vector will be orthogonal to our normal vector w.
Okay, so here is my, I don't know, some vector, well, let's call it r. It lies on the line. So these are free vectors. So this w, I can move it freely around the space, yeah, so it doesn't really matter, is it here or somewhere else. And you see that in some sense you can make a projection, yeah, you can make a projection on the direction that is described by this vector w. What will be this projection? So you can see that this vector is perpendicular to the line. So I can draw it, I don't know, I can draw it in here, for example. Maybe that will make things clearer. So this is some sort of direction. And whenever I take some vector r that lies on this line and I project it on this direction, I always get b. So you see that, hopefully, yeah. So always when I'm taking some point on this line, I'm projecting it on the direction w, I get point B. So all my points on the line, they can be described as what? So I'm taking some vector r, projecting on w is some sort of dot product, so I'm just performing a dot product, nothing, no more, no less, and I know that the result should be equal to B. So here's what I get. This is my line. What about these points? So this is my class, some sort of class blue. I have all points in here, on this side of the line. Suppose that my vector w points this way. What can I say about these points? What about projection on this vector w? Any idea what happens when I project any of these points on vector w? What do I get?
Positive value? The parallel lines, parallel lines to the cancel.
I'm getting some point somewhere here, yes? If I will project on this line. So this distance is bigger than B. Yes? So for these points of the class blue, I can definitely tell you that any of these points, I don't know, let's call them, for example, I don't know, x times w should be greater than B. Now these black points, what about them? So any of these points, if I'm trying to consider the same expression, what do I get? So I'm considering one, yes, less than B. So x times w should be less than B. So here we have it. Now, what did I get at the end of the day? First of all, if you have this sort of classifier, so I have support vector machine. Suppose for a moment that we are working with a linear version of support vector machine. In some sense, it will contain, inside of it, it will contain parameters, parameter b and parameter w. So that's what I have in there. With these parameters, I can do a classification. How do I do that? What is, in this case, a classification? So when I have trained my classifier, this was my data set, okay, I have trained it, I have obtained this sort of line, I have parameters of this line. How do I perform so-called inference? So when I'm asking something of my classifier, what should I do?
Check if
So which of this I should check, yeah, which of these conditions hold, yeah. So in some sense, I'm getting any point from the plane, so I don't know what will user ask me when I'm doing the inference, and I don't know, he may ask me some point in here or in here or in here, so whatever. And what should I do? So when getting some point, I don't know, let's call it some p, I perform p times w, and I'm comparing that, so I'm setting a star here, I'm comparing that with b. If I get something greater than b, I'm saying that should be classified as class blue. So this half of the plane will be classified all as blue points. If it's less than b, I'm classifying that as a class black, so this part of the plane. So that's how my classifier works. So that's basically the case. Do I have greater than b or smaller than b? Or I can calculate, I don't know, I can take b to the other side, and I can take sine of p times w minus b. So that's still okay. Okay, so that's what we have. Now the last question I want to pose. We want to train this classifier. So I want somehow to express in equations the training of this classifier, so to pose somehow the problem. So what I want to do, I want to draw, I want these points to be as far away from the line as possible. And I need some mathematical way to express this idea so that I can do something with formulae and get some sort of result, so some coefficients from here. Let's think, how do we do that? These expressions will be very helpful for us. So we already know how do we, let's say, compare, how do we understand how far is the point from this line. So I want the closest points to this line to be at the distance d from the line. I can suppose that on the both sides my closest points are on the same distance d. So I can suppose that. Why? Because if this picture becomes some sort not symmetric, so I get this line closer to this part than to that part, I can think about like symmetrizing the picture, so putting this line in the middle, in between these points. This way it gets farther from that points it was close to, and well, a little bit closer to the other side. But if you are thinking about minimal distance, disregarding the class that you are considering, of course you will want that. So, and that's quite intuitive for us. So we are trying to draw this line somewhere in the middle, so that's okay. We're doing that. So now what I want, so I want to say that the minimal distance to this line should be d, no more, no less. Okay, and this can be expressed in our formulae. So the closest point that we have should be x times w, should be equal to b plus d. So that's, I will mark it, I don't know, xi, for example. So that's a point from a data set. And this is for class yi equals, let's say, +1. Or I can have xi times w equals b minus d. So I'm doing step this way, and that's for the points of the other class. I can call it -1. So these are the equations I have. So if my point belongs to class +1, I have this sort of equation. If my point belongs to class -1, I have this sort of equation. And this is for the points that are closest to this line, so closest possible points. And we can perform an interesting few, let's say, transformations that will help us encapsulate these two equations into one. So express that for all points disregarding the class of the point. Here's how we do that. So let me rewrite the first equation like xi times w minus b divided by d should be okay, let's do it this way. I want to write that for all points, so this was for the closest points I have here. So let me write that for all points. What should I do to make these things true for all points of the data set? So this equality sign, it holds for the closest points I have in here. If I want this to be true for all points, I should change the equality sign to what? Yes, greater or equal. So that will be good. So greater or equal. If I want this thing to hold for all points with the class -1, I should change this sign to what? Yes, less than or equal. Okay. Now I'm doing the following. So I am taking this b to the other side. Here it is. I am dividing by d, and I'm getting this sort of equation. That's for the points from class equals y equals +1. I have a very similar thing for the class y equals -1. And now an interesting idea. What if I take this yi, and I multiply both parts by yi? And I do the same thing in here. What do I get? So on this side, I have yi times xi w minus b divided by d Now what happens here? So yi is equal to +1. +1 multiplied by +1 still gives you a +1. And this sign holds. So it's greater or equal than +1. If I do multiplication here, what do I get? On the left side, I have the same expression. But in here, I have -1 times -1. That gives me +1. And since I have multiplied my inequality by a negative number, I reverse the sign. So these both inequalities now are collected into one. So here's what I have. So these are my inequalities that tell me that points of my data set are lying on the different sides of this line, so that class +1 lies here, class -1 lies here. They are lying not closer than some distance d. And what I want to do, I want to make this distance d maximum. So I want to maximize this d over, of course, my parameters. So whatever I have in the w and in b. Okay, is this part more or less clear? So how we get here? So from here, it's really easy to get the let's say some sort of final expressions, because you all remember the lecture on the optimization, so you know what we did there. And we want just to rewrite this problem in a little bit different fashion to get closer to that standard form in which we already know how to minimize and how to solve these sort of problems. So that's performed quite easily. why? So first of all, we are trying to get rid of the normalization of the w. So we don't like it because that's some additional restriction and so on. So I am just redefining my w as w divided by d, and I'm redefining my b as b divided by d. Now my norm of the w is equal to 1 over d. So maximization of the distance d means the minimization of the norm of w. To make the problem even more convenient, since this is a positive number, I can write it as minimization of the norm of w squared. For some historic reasons, people even put, I don't know, divided by 2 in here. But once again, you remember from previous lectures that I am applying some monotonically increasing function to something, which means that I do not change where my minimum is. And I want to minimize this thing with conditions like this one. So I want my yi times xi w minus b I should have conditions like less than or equal. Yes, so I should multiply that by a minus sign. So and I should compare them with 0 to get to the standard form. Yeah, so I will take this one to this side and multiply everything by minus 1. So where does it get me? So 1 minus this thing should be less than or equal to 0. So that's what I have. I have what to minimize. Minimize over w and b. And here are my conditions. yi and xi are given. That's my data set. So this is a class of the point supervised learning. So I have a class attached to each point in the data set. These are coordinates in that space. So they define me the features that I have. In this case, feature 1, feature 2. Of course, we will have more. And these are my conditions. And this is the problem you already know how to solve, because we have considered that in previous lectures. And if you solve this problem, if you minimize that, and this is a really nice function, because what we have in here is some sort of paraboloid once again. So that's what we have. We can solve this thing, and we will get our parameters w and b. And if you have parameters w and b, you can perform inference with the formula that we have in here. So we can just calculate some sine of some point p that we are interested in times w minus b. So that will be my class. So that's class of p. So this is a linear support vector machine. Okay. So now let's get to some sort of pictures. Okay, so we have already posed our problem. I will show you well, some parts of code. How do we do that in Python? And some parts I want to emphasize for you. First, some terminological part. It's support vector machine, so there should be some sort of support vectors. So support vectors are the data points that lie closest to the decision surface. In the case I have showed you, so we had a line, a separating line that has separated our data set So the points that were lying closest to that line, we will call support vectors. So they are some sort of supporting our line. So, and these are the points that are, let's say, most difficult to classify with our classifier. Okay, let's check these sort of pictures. So here is some sort of data set. The analogy to what I have showed you on the whiteboard. We are trying to separate that with different lines, and what we want to do, we are taking these lines with some sort of margin. So you see here some sort of margin around these lines, and we are searching for the line which has the biggest margin. So that was corresponding to that parameter d I have showed you. Now what we do, this part basically reiterates what I have showed you. So here is the line. Here is the distance d I have to my support vectors. So these points, these encircled points, they are my support vectors. You see once again two classes, and they are separated with this line, and the closest vectors, support vectors, lie within the distance of d to this line. So here you see once again the formulae that I have showed you. So for class +1 we have this inequality, for class -1 we have this inequality. So we have seen that. And here is basically what we have at the end of the day. So we have to minimize our norm of vector w. We take it norm squared to make a little bit simpler minimization, and this is a very nice quadratic function, and this is a constraint minimization problem, and here are our constraints. So you have seen that everything on the whiteboard, so just some sort of reiteration, and you can refer to the notebook if you need these formulae. Now here how it looks like. So we have some sort of quadratic problem. So this is a paraboloid. So here we see that from the above, and these are some lines that describe our let's say constraints that we have. Now what do we do? Let's check how to do that in Python. So how do we fit support vector machine in Python? Very simple. We have in sklearn we have submodule svm, and we can import svc from there. So it's support vector classifier. We are creating our model. This svc, we define some sort of parameters. Since I am telling you right now about linear classifier, so I'm taking kernel equal to linear. I will show you different kernels a little bit later. This parameter I will explain to you in a moment. And what we do some fitting. We fit our dataset x, and we pass there y, which are the classes of our points. Here's what we get as the result. So we have a separating line. These points are support vectors. You can get support vectors from the model by using this sort of parameters. So support underline vectors underline. You can have there that, and you see the the distance from the line to these support vectors. So that's what we have. What I want you to pay attention to, let me ask you a little bit maybe a tricky question. So I have a data set. Let's suppose like this one, and I'm taking some point, let's say this point, and I'm moving that to somewhere here. What will change, if anything? So I'm taking this point and I'm moving it to somewhere here. What happens?
Nothing.
Yes, nothing happens. Absolutely correct. So if you are changing position of the points that are not support vectors, nothing will change. Do I have? Yes, I have a picture in a picture here. So if I take any point that is not a support vector, I move it somewhere around, nothing will change. Of course, I can bring it very close to the line. It will become a new support vector. Yeah, then something changes. But in here, nothing will change. That's a really interesting part, because support vector machine is basically relying only on a small number of points that we have that become support vectors. And that's basically the reason why you can use that on small data sets. So if I am increasing the number of points in my data set, you can see in this picture, so suppose I have 10 points for 2 features. You see how my line looks like. If I make 60 points, my line, well, slightly changes. Okay, it changes. I have different support vectors. But if I go from 60 points to 120 points to 200 points, almost nothing changes. So from some, so if I'm adding and adding some more and more points into my data set, at some moment, at some point, everything, let's say, stabilizes, and nothing changes from that. So I'm adding more and more points, but I still have the same or almost the same support vectors, and I'm getting the same line. So that's the reason why you may want to use a support vector machine if you have a small data set and you are considering to use something in there, so maybe a neural network or something like that, but you may think, well, I don't have enough data for some more complicated methods like neural networks. So you have a small number of data points, but a support vector machine may still help you, so it still may work on that small data set. So if you are scarce on some resources, you cannot calculate some heavy model, or you have a small data set, so support vector machine, that may be your choice. Okay. Is everything more or less clear up to this point? Okay, so hopefully yes. Okay, so what we have achieved, so let's once more reiterate. I know that it's a complicated topic, so we do that in some sort of chunks. So so we have considered a linearly separable data set. We have constructed a support vector machine there. So I have, let's say, we have some intuitive ideas how to draw a line to separate our plane. So we want some line that separates these points, and we want that line to lie somewhere far away from that point. So we don't want to touch it some part of the data set. We want it to be separated from there. And we have converted that into formulae, and we have posed a problem of minimization of quite a nice function, if it's a quadratic function, so it's really nice, with some sort of constraints. And if we solve that, we have parameters of the line, and we know how to perform a classification having parameters of that line. So that's what we have at this point. What we should do now, we should make our model, our SVM, a little bit more complicated to make it work with some more complicated data sets. So you might guess that this is a very nice case, very nice scenario. So we have a linearly separable data set, but we don't have always data sets like this. And we will tune in few more steps our support vector machine to make possible to work with different data sets, more complicated. So first of all, what we do? What if our data is not separable? Let me consider this sort of data set. So as you see here, I cannot draw a line that separates all these points into two parts. So that's not possible. But you probably might guess that we have some intuitive feeling that maybe I can still draw some lines, so I can still try to separate points with a straight line, but I should, let's say, allow some points to cross that line. To get close to that line, to cross that line, I should somehow allow them to do that. And of course, the question is, how do I do that in some sort of mathematical fashion? So how do I convert my intuitive ideas? So, okay, I know that my data set is a little bit worse than what I had before. So I can't perfectly separate that with a line, but I want to allow some points to cross that line. And now I need to incorporate these ideas into my equations, so that I can perform all that machinery and solve everything and get some sort of result. What should I do? So now I cannot demand these sort of conditions that I had previously. So I can't do that. Why? Because some points of they violate this condition. What can I do to make this to relax this condition, to make it still true for all points? So in some cases I have a wrong sign in here, so everything becomes negative. I want it always to be positive. So let me suppose I'm adding some new parameter, some psi I, that I'm supposing to be always positive to this part of the inequality. What does it mean mathematically? So what my relaxation does?
It's some sort of an error.
So I'm allowing my point here to move somewhere closer to the line, and this psi I basically defined me the distance I'm allowing this point to travel. So this xi times w, this was my projection, so my projection on the perpendicular. So this is b, so how far is my line from the origin. And now I'm adding this thing to make this part, let's say, more positive. So that's what I do. So I'm allowing that to travel some distance, some more distance, and even cross my line. But of course, that introduces me to a new problem. If I just add these parameters and I allow points to travel across the line, what will happen?
Bad classification.
Of course, I can't even train this. So basically, I have destroyed my conditions. So it's a really bad situation if I'm just adding these things and that's all. So I don't just want to add something because I'm just allowing points to be anywhere where they want. And now the line that is the farthest from these points will be not between the classes. It will be, I don't know, somewhere out there in outer space. So I can't have it even near these points because I have relaxed too much. So I need to constrain this psi I to make them some reasonable. And how do you think, what is the reasonable constraint on this psi I? Just from some sort of intuitive ideas that you have about the separation and so on. So what you want? So what will you want to demand from this psi I to be reasonable?
It should be less than d with x. We can call it.
Okay. Do we want all the points have some sort of non-negative psi I?
Probably yes.
Why? What it means to psi I to be strictly positive, and what it means to be strictly equal to 0. What does it mean for us?
If it's equals 0, it doesn't influence it. The points stay where they go.
So if this psi I is equal to 0, this means that we don't need to relax any constraint. So the point we are considering are lying on the side of that line, of the separation line, where it should be. So okay, let me draw that maybe on the whiteboard once again.
Let me check something while you're doing that. Maybe we have the wrong microphone selected because students are complaining about the quality.
Okay, check that.
Do you hear me now, or do you hear only Vitaly right now? Vitaly, say
Yeah. 1 2 1 2 3. No. Yes. So wrong mic. No.
it should be better now.
Okay, so I have all these parameters, the data set, and so on. Let me consider this point, for example. Do I need a strictly positive psi I for this point of the data set? So here's my separation line, here's my D I'm expecting. You know that now it's incorporated into W, but it doesn't really matter. What about this exact point? Yeah, absolutely correct. So that's the case we were previously considering. So everything is okay with the conditions for this point. It lies where it should be. So it's pretty okay. So it's psi I is equal to 0. That's okay. If I'm considering, let's say, this point, okay, let me remove this thing. I don't want not to confuse you. So what about this point? Do I need any positive psi I for this point?
Probably also no.
Yeah, so psi I should be equal to 0, so I don't need anything. Condition holds, it's okay. Now, what about, let's say, this point?
It probably should be negative. Same.
So my condition does not hold for this point, yeah?
Yes.
It lies on the wrong side of the line. So I should have psi I greater than 0 for this point. So now what we know, so from our all that intuitive ideas, if my points are on the wrong side of the line, and I want to allow them to stay there, and why do I want to allow them to stay on the wrong side of the line?
So classification works.
Because I have a non-separable data set. I may have some points of the black class somewhere in here, and I may have some blue points, I don't know, some one outlier in here, for example. Okay, even forget about this one. So I have some sort of one outlier somewhere here. And now I cannot draw any line that separates these blue points, this and this one, from black points. I can do that. But we all know this is just some sort of outlier. I don't want that to, I don't know, to break all the classification I have. I don't want one outlier to break me my classifier. So I say, okay, leave there. So you want to be there with the black class? Okay, do that. Despite the fact that this is a blue class, I say, I'm okay with that. And what I'm doing, I'm just giving this point some sort of positive psi I and my classifier still works. So I still have a working classifier. I'm still drawing this line and so on. I'm just relaxing my conditions, and I allow this point, this outlier, to lie on the wrong side, because I know it's outlier, so that's okay. Now, can you say me from some sort of intuitive, like your ideas, what do I want from my psi i's? So I have an array of psi i's. So for each xi, for each point xi, I have its defined class yi, so on and so forth, and I have some sort of psi I. What do I want to demand from them to make my classification problem more or less correct? Do I want them all to be positive?
No.
No, I don't want. Because if they all are positive, that means that my all points are outliers or something like that. So definitely I don't want that. So I want them, in a perfect case, I want them all to be 0. If I cannot achieve that, I want the maximum number of these psi i's to be equal to 0. Why? What it means? Just intuitively, so no math.
That they will be or negative or 0. Okay.
No, look at this. So having psi I greater than 0 for any point means that I'm treating that point as an outlier. So that it lies on the wrong side of this line. Do I want to have more outliers or less outliers?
Yes.
Of course, less, yes. I want them all to be some sort of classified correctly. Of course, I want as little outliers as I can. So this means that I want as little the psi i's to be greater than 0 as possible. I want maximal number of psi i's to be equal to 0. Because being equal to 0 means that this point is not an outlier. So all these points that have 0 psi i's are not outliers. They are living on the correct side of the line. They are behaving well. So that's good. These are good points. Of course, I want the maximal number of psi i's to be equal to 0. And just few points may be okay to have psi I greater than 0 and to be outliers and to sit somewhere where they do not belong. So that's what we have. Okay, is it intuitive for you? So what we are doing, so why we are demanding this thing? So okay, we want as little outliers as we can afford, and this means that we want as little psi i's greater than 0 as possible, which means that we want as much psi I as possible to be equal to 0. And now there's a question for you. How do you remember our previous lecture? I will be performing minimization now with respect, of course, to parameters of this line, but I should draw somewhere this line, and to psi i's. So psi i's should be somehow restricted. How can I mathematically express the idea that I want my psi i's as much as possible to be equal to 0. Who can tell me? So at the end of the previous lecture, I have showed you some tool that allows us to do something like that.
Lagrangians.
So what did we do with all that Lagrangians and so on? What did I introduce to you? Which tool that allows us to set them to 0? No? Regularization. Remember, regularization. We had two different regularizations, at least the ones that I taught you. Can you remember which ones?
L1, L2.
Yes, L1 and L2. What did they do to parameters? What happens when we use L1 and what happens when we use L2?
With L2, parameters become 0, as I remember some parameters. With L1, no, okay.
With L2, we are like trying to squeeze all the parameters closer to 0. So both regularizations are trying to make our parameters smaller. That's okay. But you remember with L2 regularization, so what did we have?
We decrease number of features.
Yes, with L1 we decrease the number of features. Because why? If I have L2, so I have some sort of function that I minimize. So these are level lines. And I had, with L2 regularization, I had some sort of ball in here, so with some radius r. And I was restricting my parameters to this ball, and we had our minimum somewhere in here. So I drawed you some pictures. So if I have some parameters and I have some strength of the regularization, yeah, for L2, how did it look like? So I had some sort of parameters, some strengths, I don't know, alpha. Here we will call that, okay, I'll tell that later. And we will seeing this sort of picture. So my parameter was just some sort of increasing and getting closer and closer to 0. So here can be some different parameter and some different parameter, and that was our picture. Now, let's recall L1 regularization. What did we see there? So once again, I have a function that I want to minimize. Here are level lines, but now in L1 space, my sphere looks like this. And when I'm touching it somewhere on the corner, so it's a little bit bad drawing, yeah? So I want to show you that I will touch that in the corner. So suppose I do it like this, I will get one of my parameters equal to exact 0. And when I was drawing parameters from the strength of the regularization, I had a picture like this one. So I had some parameter, at some point it drops to 0. And it stays 0. And this is a very big hint for you. What should we do to get many, many sigmas equal to 0, exactly 0?
We should do this regular regularization with
Yes.
L1.
Yes, we should do L1 regularization. And now I will show you the equations that we have. So here are our equations. So hopefully you remember that when we are performing this regularization, we are adding something to the Lagrangian, to the function that we minimize. So here is what we add, the sum of the absolute values of psi i's. So hopefully you remember that from previous lecture when we added absolute values of our parameters of the line when we are performing linear regression. Parameter C is the strength of the regularization. This is the same parameter that you have seen in Python previously in the code that I told you that I will show it to you later. So now the time has come. Here is this parameter and here is its meaning. It's the strength of the regularization. And what you have at the end of the day is this sort of problem. So I have a regularized problem. I have some part that basically makes my line pass and separate my points. And I have this part that regularizes my problem. And it tells to me that I want some outliers, but there should be as small, the number of outliers should be as small as possible. And here are my conditions. So I want my psi i's to be greater than 0. And I want, of course, my previous conditions that tell me that I separate my points correctly to hold. But now you see the psi I that I have added. So I have a little bit relaxed this condition, but I have regularized it. And this is the sort of the Lagrangian that we have at the end of the day. So this is my original function with the regularization. You remember that Lagrangian is some sort of entity that I construct from my conditions and the function that I minimize. And here I am adding my conditions. So this is this one condition, so psi I plus and so on and so forth, so that my points lie correctly. This is condition that avoids me using absolute values. So I don't want absolute values in here. It's a little bit complicated to minimize that thing. So I'm just adding it like one more condition. And what I have at the end of the day, you see this Lagrangian. And do you remember how these lambdas are called? So I have constructed this Lagrangian.
Multipliers.
I'm sorry, I didn't hear.
Lagrange, like
Yes, Lagrangian multipliers or dual variables. Yeah, that's they are. So here we have it. So here is our Lagrangian. We can do something with that, and we can minimize our new problem. And well, let's check how it works. Here is my data set. It's not linearly separable. So I can draw a line that perfectly separates my points. But I can draw some lines that, well, allow some outliers and separate these points, let's say, reasonably good. And here I'm trying to do that with support vector machine. And I'm changing that strength of the regularization C, and I'm trying different parameters. Now let's reiterate one more thing. If I have this C, and suppose I'm taking a very small c, what does it mean? So just some sort of, let's say, hand-waving way of reasoning. So C is the strength of my regularization. The bigger is C, the stronger is regularization, yes? The stronger is regularization, then what happens?
More Signs is also will be 0.
Yes, absolutely correct. So bigger C, stronger regularization, the bigger number of psi i's are equal to 0, the less outliers we have. But we are more strict to our, let's say, classifier. The smaller is C, the less is strength of the regularization, and I allow my points to move somewhere and even to cross the line. So if I have this sort of data set, I may want to reduce my C. So if I have a very big strength of the regularization, maybe I will not be able to train my classifier on this sort of data set. So maybe I will need to make it a bit lower. And here is an example of using different C's. So for example, C equal 10 and C equal 0.1. And now you see what happens. Here we have a very strict conditions, and you see that the closest points are chosen as well, support vectors. In case of a small c equals 0.1, I allow to choose my machine some different points as support vectors, and some of these points are, well, getting closer to the separation line. So that may be, in this case, you can allow some points to move closer to your line. And in some different cases, you may allow your points even to cross this line and to live on the other side. And that will be okay. Here is a demo for you. That's how support vector machine works in sklearn. So I will show you how that looks like. Okay, how much time do we have before break?
Just 3 minutes.
Great. I will show to you this demo, and then we will go to break, and then we will continue with kernelized SVM. Perfect. Okay. So let me put some points here, class A, class B, and I perform classification. Here's my separation line. You see that this point, and this point were chosen as support vectors. So that's okay. Here are my parameters. I'm using linear kernel. After the break, I will show you which different kernels we can use. And I'm using C equals to 10 to the 5. So what it means?
Very strict.
Yes, it's a very large C. So my regularization is really strong, and it does not allow any points to cross this line. So if I'm trying to put a red point somewhere here, well, I can get some sort of problems. Maybe not enough strength, so let's change it to 10 to the 10 even. Why not? It may even happen that SVM refuses to train on these data. So now you see the problem. So it did something, well, very strange. Now what can I do? Let me make this C smaller. So make it, let's say, 10. Now I allow my points to be on the wrong side, and I retrain my classifier. And you see that it performs, well, reasonably good. So it's reasonably nice situation. Let's take some sort of these data sets. So I'm mixing some points in here on the boundary, but you still see that I can reasonably separate my points and drawing a line. And you see it works more or less, but it still works. Now all these points are designated as support vectors, so they all are closer to the line than this sort of distance d. But if I make my regularization strength bigger, I can perform once again retraining. As you see, it takes a long time because it's really hard to train. So I guess SVM even cannot be trained on some data sets. So maybe I have guessed this sort of case and it will fail. Well, no, it didn't, but still we have some sort of strange case. And this is basically the case of support vector machine with so-called soft margins. So we have considered with you a simple support vector machine. Now we have considered a support vector machine with margin softening. So this old technique with OZC and so on is called margin softening. And after the break, we will consider with you SVMs with kernel. So okay, let's take a break and then we will continue. Okay, so now we have considered support vector machine, a linear support vector machine, and we have seen how to solve the problem if we have, well, let's say a data set that is not linearly separable, but in a sense that we can relax our conditions a little bit, so we can softening our margins and still get some sort of nice result. Now we are going to make our support vector machine even better. So I will show to you that support vector machines are capable of not only drawing some sort of lines or planes or hyperplanes and so on and so forth, but they are capable of creating separation surfaces of quite a complicated form, and we will see how to do that. Of course, we cannot do that with that linear support vector machine that I showed you. So we need to change something in there. So, okay, what are we trying to do? We will have some sort of data set that is not linearly separable, like this one. And we will see that there is, well, there's actually no way to draw some line through this data set that will work for us. So we cannot separate that with a line. So let me wait until the support vector machine trains and shows us some result. That should be some really bad result, or maybe it even will be not able to train. Let's check that. Okay, so here is the result, and you might guess it that drawing straight lines will not help us to get some sort of separation in this data set. So we want to do something quite different. And that will be performed with using so-called kernels. So here is parameter kernel in the support vector classifier. I'm setting it to RBF, so-called radius basis function kernel. I'll show to you in a moment what that is. And now I'm using my support vector machine, and you see that it separates my points nice and clearly. So I have some sort of separation line. In this case, it's not a straight line, it's some sort of closed curve. And inside of it, I have one class. Outside of it, I have different class. Once again, you see support vectors encircled with this yellow, so on and so forth. So what we are going to do right now, we are going to get into details how this kernel equals RBF, or there are a few different kernels available to you in sklearn. How do they work and what everything that means. Okay, so the first step we do, let's put it this way. I need to do a few mathematical steps that at first glance, it's not clear where do they lead us. Why do we do them? but at some point, some interesting property will emerge, and I will show you that this property basically saves the day. So it makes possible for us to use that kernelized support vector machines. And basically, support vector machines with kernel, it's the main, let's say, version of support vector machines that we use today. Because without that kernel, they will be actually useless, I will say to you. So it's really hard to find data sets that are nicely separated with some sort of hyperplanes, even with that margins softening, so on and so forth. So we need a kernelized version. So it's really crucial part. So let's get to it. First of all, we have already constructed a Lagrangian with you. So we have a Lagrangian. We are minimizing that. That's okay. Now, we are recalling one of our previous lectures, and I want you to remember that when we are performing minimization and we have a Lagrangian, we are basically posing a so-called primal problem. So I'm minimizing my Lagrangian. I'm taking some sort of infimum with respect to some sort of parameters, in this case, W, vector W and B. And it looks like I have some sort of formula that look like infimum with these parameters, WB, psi I, then supremum with respect to dual parameters, lambda I and eta I, and I want them to be positive, and there are some complicated formulas inside these brackets. So you saw that formulae, just know that there are some expressions. Okay, now how does the dual problem look like? What should I do to make this problem dual? We can always transfer from primal problem to dual problem. How do we do that?
At parameter?
No. Recall that primal problem, in the primal problem, I had some sort of expression. So I had some, I don't know, where is it in here? So here's my Lagrangian. You see that this Lagrangian is supremum with respect to dual parameters, lambda I and eta I. Hopefully you remember why do we do this supremum. What does it do for us?
Because it makes a more strict Lagrangian, and so, yeah.
Recall a previous lecture. So this supremum basically makes our conditions work. So we had a problem. We wanted to minimize something. So for example, here is the expression that we want to minimize. And we had some conditions. So we want these conditions to be fulfilled. And what did we do in this case? Recalling this supremum, well, here is a little bit, I need to multiply this by -1 to make this condition to put them to standard form, to make that less than or equal to 0. But I want you to recall the fact that I am incorporating these conditions into Lagrangian, and I'm taking supremum to get the following effect. When my conditions are fulfilled, remember these lambda i's, they are always bigger or equal to 0. When my conditions are fulfilled, this part with this minus sign, it is negative. So taking a supremum will mean that I will set lambda I to 0. So if this condition is fulfilled, yes, so this thing is positive. This thing is positive. So this part here is positive. Lambda I is positive. But here is a minus sign, so it makes my overall Lagrangian, it makes it smaller. What should I take lambda I to make a supremum, to make it bigger? I should take it 0, yes? So lambda i's are positive. If I am multiplying some positive value by something positive, something strictly positive, I will get some positive value in here, and I will take, well, my Lagrangian minus some positive value, so I will make it smaller. If I don't want it to be smaller because I want supremum, I want it to be bigger, I need to somehow neglect this part, remove it. And I can do that by taking lambda I equal to 0. So this part will disappear. And if this condition is fulfilled with psi I greater or equal to 0, this part will disappear. So, and I will get only this function that I have here in my brackets. So when conditions are fulfilled, my lambda i's and eta i's, they disappear. They are basically removed. And I am minimizing my function, this one. If my conditions are, in some sense, are bad, are not fulfilled, so I don't get here bigger or equal to 0, I get some negative value here, what will happen when I'm trying to take this supremum? So I have a negative value here. I have minus sign here. So whenever I set this lambda I to some positive value, I'm adding something to Lagrangian, yes? So I'm making it bigger. And if I'm trying to take a supremum, I will take that
give infinity.
Yes, absolutely correct. It will explode. So what it means, if my condition, if that happens, that I stepped on the point, because I'm minimizing with respect to these parameters, I will minimize this Lagrangian. So I will try different points in this space of parameters. And if I step on the point where this condition is not fulfilled, so it's wrong, it does not work, my Lagrangian explodes, it goes to plus infinity. If I step on the point when this condition is correct, my lambda I becomes a 0 and is effectively removed from the Lagrangian. And what is left only the function that I minimize. This means that this supremum, it basically makes what? The parts where the conditions are fulfilled are left as they are. So I'm just minimizing the initial function that I had, this one. But the parts where my conditions are wrong, where they are not fulfilled, my Lagrangian explodes and I get plus infinity. And if I perform minimization of the Lagrangian, I take an infimum of that Lagrangian, what will I get?
Original function?
I will get minimum of this function, but only in the region where these conditions are fulfilled. Because if this condition does not work, I get plus infinity. Any finite value will be better than that plus infinity. So all those parts where these conditions do not work, they disappear when I perform minimization because they give plus infinity. And whenever I have a point where I have some finite value, it's much better. So of course, they just disappear from consideration. So this is the reason why we have this supremum. It makes our condition work. And well, we're getting, if it happened that I went into all these things, let's note, please, that these lambda i's, if they are equal to 0, this means that conditions are fulfilled. I don't need these psi I, and this is just a regular peripheral point. So that the point that does not cross that line, it does not make something bad. It's a really nice point that is outside of that street that we draw around our line. If lambda I is from 0 to C, it's a marginal support vector. and if lambda I is equal to C, its support vector that is violating the borderline. So that's what we have. We can classify our support vectors by looking at these lambda i's. Now, okay, what do we have at this point? So we have this sort of Lagrangian. We understand that we need the supremum to make our conditions work. So it just makes our Lagrangian to explode at each point where they are not fulfilled. And now I'm trying to minimize this Lagrangian. I'm taking infimum of the Lagrangian. So my primal problem looks like I take infimum of supremum of that complicated expression. Here is my primal problem. Now recall, how do I transfer to the dual problem? I switch places. I just swap supremum and infimum. I just swap them. So I get the problem where I first take infimum with respect to these parameters like vector w, b, psi I, so on, from the same expression. And then I take supremum. Do we have any reasons to say that I will get the same minimum? In a general case, no, we don't. So it was in our previous lectures, I showed to you that the primal and the dual problem, they do not always coincide, but in some cases they do. We have some theorems that tell us even in, well, that if we have a nice case, then we can prove that primal and dual problem coincide, so on and so forth. In this case, they do coincide. We are lucky. I will not prove that. I will just tell you that we are lucky enough for the primal and the dual problem to coincide. That has to do with the form of the minimization. It's a really nice function. That quadratic function is a really nice function. So taking into account that it is quadratic function, we can prove something and say that, yes, our dual problem will give us the same result. Now what do? I have this dual problem. I have supremum of infimum. I am considering infimum. In some sense, I'm trying to minimize what I have in these brackets, this complicated expression, where is it? Here it is. So this complicated expression, I'm trying to minimize it in some sense with respect to w, b, and psi I. I do it the calculus way. So I'm just taking the derivatives, I'm setting them equal to 0, and I'm looking what happens. So nothing fancy here. So just calculus 1. If I do that, I will get these sort of expressions. So we had a really complicated Lagrangian, but you see that these expressions are quite simple. Now what I'm doing here, I have these expressions. I can, from them, I can substitute them into in here and get my dual Lagrangian. So I have performed that minimization. I substitute them back into these brackets, and I get everything in here. So supremum is left out. We are doing supremum of dual Lagrangian, and here we have it. Looks really simple. Here I update my constraints. So once again, I'm just using these expressions, and so I'm substituting them back in whatever I had previously, and I'm getting a new Lagrangian. I'm getting new constraints. And this is my dual problem. This is my dual classifier. How do I perform classification? Well, substituting back, I can get this sort of expression. So calculating sine of f of x, x is the point that I'm checking, which class it belongs to. I should calculate this thing, and the sign of this function will tell me to which class it should belong, to +1 or to -1. Here is an example to how to calculate b. You might notice that it was somewhere lost in our calculations. That's okay. When you are performing that derivatives, you can check that. But here is the way how to recover it when we transfer to the dual problem. Okay, so what did we get at the end of the day? So we have transferred to the dual problem. And here is a very nice property that we will use in a moment. So I want you just to make notice of it, and I will show you how that plays out when we move further with kernelized SVM. You see that all expressions we have here, they all contain scalar products of x's with different, let's say, data points, or scalar products of data points among themselves. We do not see bare x's here. They are all incorporated in some sort of scalar products. I want you to notice this part, because that will play a crucial role when we move to considering kernelized SVM. That's the reason why we can even build that kernelized SVM so easily, because otherwise we will have some sort of troubles. So, okay, so everyone noticed we have scalar products everywhere. If we know scalar products, we know everything that we need. Now let's get to the problem of constructing kernelized SVM. Here is an example of a data set that cannot be separated by any line. You see here. We need just one more idea to get to all that kernels and so on. So we have all the mathematical machinery we need, or almost all mathematical machinery. Now we just need some intuitive ideas, and we will be there. So let's check this out. So this is a data set I cannot separate with any line. Here is the idea that helps us to do this separation. Suppose that I'm transferring from two coordinates. So here I have some feature 1 and feature 2. I'm transferring to a 3D space. And I am setting my third feature to be equal to sum of squares of feature 1 and feature 2. And here you see in 3D the picture what happens to all that points when I move to 3D. Is it now linearly separable or not? Yes, it is.
Yeah.
So now I can draw a plane and I can separate that points. And in this case, once again, I cannot draw any line in here in 2D to separate these two classes. It's not possible. But when I move to 3D and I set my third coordinate equal to x times y, I get this picture. Can I separate them?
Yes.
Yes,
Yes.
with the hyperplane.
Yes, absolutely correct. So I can separate them. So moving to the spaces of higher dimension may transform some data sets that are not linearly separable into data sets that are linearly separable. And that's the idea that that will take us to the kernelized SVM. So we want to transform from the space where we live to some different space, and in that space our points will be linearly separable. Then we will perform in that space basically all that SVM thing. We will get our hyperplane in that space, and then we will use it back here. Of course, you might guess that the straightforward way of transforming to some different spaces may be complicated, because transforming some vectors into somewhere, then doing some operations in there, then transforming back, it's a really complicated operation, and it's not really clearly how to choose the space, where do we transform to, and so on. But now recall what I showed you. All our equations regarding support vector machine in the dual form contain only scalar products. So in some sense, I do not need to know where exactly is my vector x transformed to. I don't need that. I just need to know how scalar products are transformed. And that's a very crucial idea. So what I have at the end of the day, so I have my initial space I have started from. I need to transfer to somewhere and do something in there. But I see that whatever I do in there requires me to know only these scalar products. So I don't even need to know where my vector is mapped to, but I need to know where my scalar product is mapped to. And it seems a very crucial part because it really helps us. This mapping of the scalar product is basically what we call a kernel. So a kernel is a function that takes you two vectors and gives you a number. If you can make a sense of that number as a scalar product in some different space, you can use that. You can already use that. You can plug that into that formulae and get the result. So that's how it works. Of course, you might ask me, well, what are the warranties that whatever function I choose, that it has meaning of some scalar product in some different space? Well, we have a really nice theorem, like Mercer's theorem, that helps us to, well, basically say whether it is or not. But it has connection to so-called spectral theory of compact operators, so we are not getting into that. But instead, I will show you a few exemplary kernels that are often used in practice, so that have some sort of practical meaning. And I will show you a few methods how to get new kernels from old kernels. For practice, that should be more than enough. Or you might get into the spectral theory of compact operators. So that may be even better. Okay, so examples of kernels. Quadratic kernel. So you take a scalar product in your original space and you are taking a square. Pretty okay. Do the same, but not square, but some order n. That's okay. Scalar product plus 1, and then to the power of n. So-called polynomial kernel. Still good kernel. RBF. Note this one. So this is very widely used kernel. Radial basis function kernel. It looks like exponent to the power of minus gamma times norm of difference between x and y squared. Looks a bit complicated, has its own tunable parameter gamma. So if you are using RBF in SVM from sklearn, for example, you can define gamma. It's one of the parameters of the function. So you can do that. What's interesting about this kernel, it corresponds to the mapping of our vectors. We are working in some maybe many dimensional space, but it's finitely dimensional space. It corresponds to the mapping to the infinitely dimensional space. So you can't even do that mapping using computers, because we are always working with some finite dimensional things. You can't fit anything infinite into computer. But this kernel corresponds to the scalar product in the infinite dimensional space. And it's really nice kernel. And you can generate new kernels by some sort of rules. So for example, you can multiply kernels and get a new kernel. So that's okay. You can do like sum with some positive quotients, alpha 1 and alpha 2, you will still get a kernel. And as you see here, there are a few rules you can use to generate some new kernels from old ones. So if you need some different kernel, you might think about generating it from previous kernels. Okay, what it gives us. Here's an example of a data set, very bad data set, but you see how that works. So we have here all these points. They are not, let's say, nicely separable. And I'm trying to do a linear SVM. Here I have a line. I'm trying to do RBF, so radial basis functions. please note how complicated is this margin between two classes. Moreover, you can even get some sort of isolated parts in here, like in here, for example. So that's okay for RBF. It's a really powerful tool. So you will probably want to use that. And you can use a polynomial kernel. So here is an example. So that's what we get. We can get a very complicated margin between classes. And that allows us to make some sort of, to separate some data sets that are not linearly separable. Up to this point, is it more or less clear to you what is happening? Yeah, good. Okay, so now probably the last part I will show you. So I want to show you how this sort of dual classifier or this kernelized support vector machine is trained. The algorithm is called sequential minimal optimization, or SMO. It allows us to, well, basically to find maximum of this thing. So you remember all that formulae that I wrote you previously. The only difference is that I have substituted that scalar products between xi and xj by kernel from xi and xj. Well, that's what I basically told you. So we had scalar product. Now I'm substituting that with kernel because kernel signifies to me a scalar product in some different space. So that's pretty okay. And I need to find maximum of this that is subjected to these sort of constraints. And SMO, as it is implemented, well, in sklearn or somewhere else, it probably contains, let's say so, some quite simple general idea and many phenomenological additions that allows it to converge a bit more quickly. Of course, I will just avoid all that phenomenology. I don't think it will be of any use for us. But let's take the general idea. What do they do that to train this sort of classifier? What is used? This SMO. It's basically a modification of so-called coordinate descent. So hopefully you remember from previous lectures that we can perform minimization with coordinate descent. That means I am doing minimization with respect of some chosen axis. And for example, in two-dimensional space, I'm trying to minimize with respect to x, then with respect to y, then with respect to x, then to y, and so on and so forth. I'm doing that, and at some point I get to some sort of minimum. This is a slight modification. I'm using not one, but two axes. My axes are basically correspond to parameters lambda, because I'm maximizing with respect to lambda. And I'm doing that having in mind that I want these conditions to hold all the time. So I want my lambdas to lie inside some square from 0 to c, or it will be some sort of hypercube in case of many lambdas. And I am taking the lambdas I'm minimizing with respect to lying on some line, and I'm searching a minimum for that line, and I'm always concerned with the fact that they are constrained with this parameter c. So it's really easy. I just randomly choose some two lambdas, and I am performing minimization with respect to that lambdas. Why it's so good for me, that minimization with respect to two lambdas? Because I can express that analytically. So I can write formulae analytically and, well, definitely say that minimum will be achieved when lambda I is equal to something, lambda j is equal to something else. Now I will show you a simplified, this sort of simplified version of the algorithm as I have implemented So this is a sort of my implementation. So I don't think you will find it somewhere else in this form. Of course, SMO is well-known algorithm. You will find it somewhere, but this sort of simplification that I want to show you, it's handcrafted. So probably you may want to see that if you want to implement your own support vector machine with kernels and so on. So it's really easy to do in, I guess, 30 lines of code even. So what do we do? So in simplified in simplified SMO algorithm, first we form a matrix K that has this form. So I am taking kernel from all possible pairs of vectors in my data set, some x1 and x1, x1 and x2, and so on and so forth. And I'm multiplying that by their classes, y1, y1 here, y1, y2 here, and so on and so forth. Now, what do? I can rewrite my dual Lagrangian in this form. So I'm some sort of performing summation with respect to all indices. And I'm thinking that I will work with some lambda m and lambda l. So I'm some sort of taking them out of that summation. I'm taking them out, and I'm getting this kind of expression. So here that m and l parts are taken away, and I can treat them separately. If I write it in this form, I can perform minimization with respect to these parameters when they are restricted to this line. So all points lying on this line, they mean I do not violate the condition, this condition. So the sum of yi lambda I is equal to 0. So all the points lying on that line, they do not violate this condition. I take minimum, just plain old calculus 1 style. So I do all that derivatives, so on and so forth, and here is the result that I get. And I can find this value of parameter t. So I'm describing my points on this line in the vector fashion. So I'm taking some vector u. I can multiply that by parameter t. I have some initial point in here, some v0, and I can describe all the line by changing my t from minus to plus infinity. I'm substituting this form in there. I'm performing all the derivatives, so on and so forth. And at the end of the day, I get this sort of parameter t that corresponds to the minimum of my function. So here it is. Well, if you are familiar with Newton method, this should be more or less familiar to you, this sort of expression. And now I'm just concerned with the fact of restricting my lambda m and lambda l nu to 0 and to 0c. So I just need to perform restrictions. So when I was moving along this line, I found this point. This is my minimum. I know that my function is increasing if I am getting further from this minimum, either it be on one side or another side. It's monotonically increasing. It's a quadratic function. So my perfect, let's say, minimum with respect to this restriction of parameter c should lie on the border of this square. So if I get this point inside the square, everything is okay. If I get it outside, I should move a little bit closer. I should sit on the border of this square. And this is my new lambda m and lambda l. And now I can perform iterations choosing some randomly l and m. I can choose them randomly, but do that many, many times. And I'm updating them. At each step, all my conditions are fulfilled. So I have this sum equal to 0. I am always concerned with restricting my lambda i's to this segment from 0 to c. So everything works. And at some point, I get my result of my minimization after many, many iterations. So here is a comparison to sklearn of the simplified algorithm. You may see that it differs just slightly. And here I want to show you implementation in JavaScript. So let me put some points in here. And you see that we already have a separation line. I can change the restrictions on border, and I can change my kernel. So here is a different kernel. So here is a RBF kernel. If I'm moving some points around here, you see how boundary changes. So you can see some sort of different effects by playing around with this demo. So I encourage you to check that. For example, if I'm taking some point that is not a support vector, what happens? I move it around and nothing changes. If I move it too close to the boundary, it becomes a support vector and it starts changing my boundary. I can transform that into an outlier if it crosses the line. So here it is. I can use different kernels and I will get different lines depending on the kernel I chose. And I can use different restriction on the parameter c. So let me make c bigger and bigger. It's 10 to the 4th now. And now you see that what my restriction has done. So you are recalling that this c is connected to that sort of regularization. It is strong enough now to require all that size to be equal to 0, which means that I do not allow points to cross my boundary or to get too close to that boundary. And you see how my result of classification looks like. Probably this is not what you want to see in a practice, yeah, because this point, for me at least, looks more like an outlier. So you probably may want to alleviate this condition, make C, let's say, smaller, and for example, get the result something like this. So maybe that will be result of your choice. Or maybe the problem is so that you want to restrict that. So that depends. So this is what we have. Okay, so I guess I have some problem of implementation, this sort of algorithm in workbook. If you wish, you can try that. And I guess right now we are more or less complete with all the internals of the support vector machine. There are a few points I will emphasize to you, but they have nothing to do with math, so probably we have moved through all that heavy machinery. And maybe if you have some questions or some concerns at this point, it's a good time to ask, probably, before we have shifted our attention to somewhere else. Is it more or less clear what is happening? What are we doing?
More or less.
Okay, so more or less clear. Okay. So now we know how to create a support vector machine with kernel, with soft margin, so on and so forth. So it's really machinery that we can even implement that, and we can make use of that. And of course, we have some implementation done for us in sklearn that I have shown to you. Now, we have some sort of modification of support vector machines and some slight changes. I just want you to be aware of. I am not getting into any details. So There are some sort of modifications like LSO SVM, some doubly regularized SVM, so that SVM is elastic net, support features machine SFM, relevance features machine RFM, or RVM, relevance vector machine. They all are implemented to alleviate some problems, because in some cases too much points are becoming support vectors, so too much freedom to bend to fit the training data, and we have a problem with the generalization. So we know if our model is too flexible, we don't get any generalization, and we are getting some overfit. We're not getting the result we want. And there are some methods to implement some automatic features to avoid these issues, but I guess you should check that the book by Vapnik, 1995. So it's some sort of adding a penalty function for mistakes made after training, and that can be used to make our SVM a little bit better, or you can use one of these methods that I told you. Interesting thing, you can modify SVM to perform not only classification, but regression. Maybe you can guess that from some, I don't know, some intuitive ideas, but before, in the classification problem, we were concerned with the fact that I have some points of my data set, I'm drawing some lines, and maybe some curved lines, or whatever, and I want my points to stay away from that line. But what if I reverse the problem? I have some points on the plane, and I want that points to stay as close as possible to my line. And that's pretty okay. So I can still write almost the same formulae that I wrote for you, but instead of requiring my points to stay away from the line, at least distance d, I can require them to stay close to the line, not further than some distance d or epsilon, if you wish. And we can build all that formulae based on this new requirement, and we will get support vector machine regression. And here is an example how it works. So here is an RBF model that works on the data set. It draws some line. Here is a linear model, and here is a polynomial model. So you can perform even regression with SVM. Another problem that you may be concerned with, I have presented to you support vector machine as a binary classifier. But what if we want more classes? In some sense, this is really a problem, because in its heart, SVM is a binary classifier, and it's nothing you can do with that. So the formulae I have presented to you is exactly the formulae that work there, that are under the hood of the SVM you have in sklearn. So how do we solve that? We can think about different approaches. Maybe the most common one is so-called one versus all approach. So when you are taking one class out and you are training a classifier that classifies a point, does it belong to this class or to some different class? And you have, for n classes, you will have n such classifiers, and you will check each point with respect to each of these classifiers. Of course, that has some more problem. You get some different problem to that, because your data set becomes very, very unbalanced. If you have 10 classes, you will have 10% of your data points in one class, for example, and 90% of points in all the rest classes. Of course, that creates you some sort of unbalanced data set, and that may cause you troubles. And of course, there are some methods to work with that and to do something with this problem. Well, another problem, another approach may be training some sort of classifiers. Here is a nice picture for you. Here is one of the problems when you are training, for example, two classifiers, like class C1 and not C1, and class C2 not C2. And you see that there may be some areas when you are not certain which class it is. So that may be a problem. You may try to train more classifiers, like each class versus each different class. And you can try to use that to classify your points for many classes. But still you have a problem like on this image on the right. So I have 3 classes, and I'm training C1 versus C3, C1 versus C2, and C2 versus C3. But I still have some region where I cannot definitely tell you which class it is. So this classifier tells you it's C3, this classifier tells you it's C2, and this one tells you it's C1. So which one it is, we don't know. So yes, there are some problems if you have more classes, but I guess in practical cases it may be neglected more or less. Despite the fact that you still have some new articles coming up and people are still trying to do something with this problem. And here are even some references I have put for you, what to do with all that things and what are people trying to do. So maybe there are even some more or less new one, like from year 2000. Maybe there are even newer. I guess I should check that on my own. And here is the demo for you. That's an SVM with arbitrary number of classes. You can put more points in here, so you can put points of class 1, some class 2, I don't know, class 3, and you can try to classify that. And here is how that classification looks like. So what is that? That's linear kernel. You can use a different kernel, for example, RBF. So I encourage you to play around with this demo as well and check how that classification is performed, when it's performed good, when it's performed bad, and what else is happening. So just to make some intuitive sense of all that regions and what do you get when you perform different classification. Okay, here is just some simple example when we are trying to classify faces with SVM. Not getting into that because I'm using here so-called PCA. I will tell you about that a little bit later. So it's just compressing data in image into some manageable amount of components, in this case 150. I'm performing support vector classification, and what I get at the end of the day is almost perfect classification. Here is a so-called confusion matrix and you might see that it's almost diagonal. So more or less it's working. So even for such a complicated data as an image, as a face, we can still fit that into support vector machine, and it still works even on quite a small data set. So it performs its work. So now what do we have at the end of the day? So we have studied our support vector machines. They have their advantages. Their dependence on relatively few support vectors means that they are very compact models and take up very little memory. So if you are working with some devices, so maybe you work with some embedded programming, so whatever, so something that is scarce on resources, you may want to use support vector machine if you cannot fit some neural network into there, and so on and so forth. So maybe support vector machine will be the model of your choice. So once the model is trained, the prediction phase is very fast. So you have seen that. So we are just calculating, in case of linear support, linear support vector machine, we are just calculating some sort of one scalar multiplication, and that's all. In case of even kernelized support vector machine, we are just calculating few kernels and adding something, and we get the result. So it's really easy to do. It's really quickly to do. So that may work even on some really old devices. That will be great. The result is affected only by points that are near the margin, so only by support vectors. And that's why they work well with a high dimensional data. So even data with more dimensions than samples, which is really challenging for all the different algorithms. So I told you that in practical cases, we will be mostly willing to have more data points than we have features. So at least like a rule of thumb, we will want at least 5 times more data points than features. But as you might guess, support vector machines are capable to do something even in cases when you have more features than data points. It's still possible to do something with that. And it's very versatile, and it's able to adapt to many types of data with the help of that kernelized approach. So that's really good. Of course, they have their disadvantages. So it's not everything is so good. So the problem is the first problem is scaling with the number of samples. So in worst case, you have n cubed time of training. Or for some efficient implementation, n squared. So for a large number of training samples, this is quite, it's not good, let's say so. So we don't want that for a large number of samples. So that's minus. Result is really strongly dependent on the parameter of C. So softening the margin and how much are you softening that margin is really a crucial question. So in most cases, you will want probably to choose this parameter very carefully, and maybe with via the cross-validation procedure. That may, of course, take some time before when you perform all that cross-validation and so on. And the problem is that if you are using all that methods, the results, they do not have some direct probabilistic interpretation. So in case of naive bias, you can perform some interpretation of your results, like the probability of getting something this and that is like this and like that. So this model does not allow you to perform that interpretation, and this may be a problem in some cases. So yes, that may be the problem. Okay, so with that being said, I guess it's everything that I wanted to tell you today. If you have any comments, questions, please. No, I guess no comments, no questions. I guess you're tired from all that formulae. Yes, please.
Some different understanding how different kernels geometrically classify our.
How do they help us to classify? Well, the first thing, maybe I will return to this image. So here is the picture I have showed you. So this is the transformation to that different space. Well, maybe I'll try to draw something on the blackboard or the whiteboard. Okay, so what do we have? So here is my, let's say, data set that cannot be, that is not linearly separable, well, by any means. So here is my class black, here is my class blue. That's what we have. I want to separate that somehow, but I cannot do that with any line. Suppose now I have some sort of transformation, some function f, that takes me to a 3D space, and that maps this point in such a way that I have these points mapped somewhere in here, and these points I have mapped somewhere in here. So now this thing is linearly separable. So that's the part I have already shown you. So I can draw a plane, and this plane separates my points perfectly. Now, what is this function doing? So it's working from the space where my original data set lives in. So I don't know, some Rn, for example. and it maps me somewhere to some Rm, for example. If I want to perform a classification like this one, what can I do? I can, well, the simplest way, maybe, without any complicated math, what can I do? I can just remember this function. So I have somehow found this function. It looks nice for me. So I can use when I can train my classifier in this space, and whenever someone asks me about the point somewhere here, I can just transfer that with my function f into here and perform my classification in this space. But that's not really convenient for me. So it's not very convenient. And it just happened that when I wrote all that my equations, all that complicated equation, it turned out that all these functions, they depend only on scalar products. So to find a classification here, so I do some classification. I class, for example, from that x. This is some sort of function that maps me my x in here into a class to +1 or to -1. So in here or in here. It contains, when I write an analytical expression for that, it will contain only x scalar product with some points from the data sets, some xi's. It has no free x, it has nothing to do. It has only these sort of scalar products. So I can think, well, why do I calculate this function on my data point to transfer it here and then calculate all these things? Maybe I can avoid that altogether and get from here directly to here. And the function that will transfer me from here to here, so without getting with the help of function f, so before I was using f to get in here, then I was using scalar product to get in here. So I was using that scalar product. Now I say, well, I can get here directly. Why not? And this function will be called kernel. So this is kernel k of the data of my x, for example, and I don't know, some xi. So this is the thing I want. So everything in this classifier, well, it's multiplied by some coefficients, something adding, something subtracting, so on and so forth, but it always boils down to this sort of scalar products. And I'm, of course, doing quite a natural thing. So why do I need 2 jumps to get in here, then in here, if I can make 1 jump and do just calculation of kernel? And that's my kernel. And the interesting part in all of this is the fact that when I'm using this kernel, so I'm using this kernel to get in here, I can avoid this space altogether. I don't really need to know where did I map this point in here. I don't need that. I need this thing. Kernel gives it to me. Why do I need this? I can forget about it. And it's really convenient, as it turns out, because for radial basis functions, for RBF, this space will be infinitely dimensional. I can't fit it into computer. It just hasn't infinitely dimensional memory, so I can do that. But if I need only this part, it turns out that kernel is quite a simple function. I'm doing some sort of exponentiation, some parameter minus gamma, some difference between vectors, some square, looks really simple. And I don't need this space anymore. So here is the main idea, and I will say it's even ingenious idea, to get from primal problem to dual problem, to see that all we need are these sort of scalar products, and then to understand, well, if I have scalar products, I can directly transfer from my initial space to this scalar product, avoiding getting to this complicated space. So that's the main idea of these kernels. And as you see in these complicated spaces, it might happen that you are dividing your points with planes. So here our support vector machine is working as a linear support vector machine. But in this space, it will look very, very different. Because of course, if I'm transferring to here, if I will transfer this plane into here, I will get something very, very different. So that's how it works. Okay, so hopefully that clarified something, or there are any other questions. So please feel free to ask. I know it's a complicated thing and SVMs are not so simple as they look at the first glance, so maybe no more questions, I guess. Okay, if we have no more comments or questions, I think we are done. So have a nice weekend and see you next Friday.